So just quick review what we talked about last time. We just went over these properties, right? We just said that the commutative property, to commute means to exchange. So let's click and close here for a second, please. The commutative property, if I have two things that are being added, I can flip the order in which I'm adding them. That's it. Commutative property for multiplication, if I'm multiplying two things, I can, once again, I can exchange the order of the product. Associative property involves more than two things being added or multiplied. And that just tells me that I'm free to group the things that I'm adding or multiplying however I want to, okay? Distributive property, you've seen about 1,000 times. Identity property, remember there's this unique identity number for addition and multiplication so that when I add it, I don't change the identity if I add it to something. Or if I want to multiply something by this number, I don't change that something. If I start off with A, whatever it is, if I add 0, it stays A. If I start off with A, whatever it is, and I multiply by 1, the value remains A. Okay, so we preserve the identity. There's a connection, remember, between the identity property and the inverse property, and they go together. They both start with I, so we remember they go together. The inverse property just says whatever A is something, what would I add to it so that the result is 0, my identity number for addition. And what we said was it's the opposite, right? The additive inverse is the same thing as the opposite, okay? For multiplication, same question. What could I multiply something by, or something we'll call A, so that we end up with the result being our special identity number for multiplication, which is 1. So the multiplicative inverse, we found out, was the same thing as the reciprocal. Okay, give me thumbs on that. Up, down, sideways, how we doing? Okay, a couple quick practice questions on this. Did we do, this isn't from us, right? No, this isn't from, I think I'm on the wrong thing here. Period. Oh, what the heck? Okay, I put last period stuff, I put it in the wrong place, that's all. Let me just delete all this. I want to do that. Okay. All right, so what's the, and everybody just, I tell you what, everybody take turns on this. Everybody try to answer at least one of these. So just raise, I'll just go by show of hands. What's the commutative property for addition? Using A's and B's and C's if necessary. What do we got? What's the commutative property? Yes, clear in the back. What do we got? Yep, go ahead. There you go. A plus B equals B plus A for multiplication. Go ahead. Good, equals B times A. Okay, let's see. Lau, I'll let you take the next one then. What about associative property for addition? Okay, A plus the quantity, B plus C equals. Very good. Okay. How about for multiplication, somebody? What do we got for multiplication? Somebody different. Go ahead. Okay. Let's try that. Oops. This isn't working. There we go. A times the quantity BC equals the quantity A times B times C. That's what you said, right? Okay, good. The identity property for addition. Somebody? Yes. Good. A plus 0 equals A for multiplication. Yes, ma'am. A times 1 equals A. The inverse property for addition. Somebody want to take that one? Go ahead. Okay, good. A plus its opposite equals 0. And remember where we're getting that 0. It's because it's the identity element, right? For addition. Okay, what about for, very good, what about for multiplication? The inverse property. Go ahead, Kylie. There you go. 8 equals what? Not 0. No, what's A times its reciprocal equals 1. There we go, right? And remember where we get that from? It's because, whoops, how come that won't change? Because our goal here is to get back the identity number, right? So for multiplication, we're just answering the question, A times what gives me back 1? It's reciprocal, okay? And then the distributive property, you guys know that one. You fill in the blanks. A times the quantity, B plus C equals AB plus, there you go. Okay, now we're playing the game, name that property. It's a great game. Name that property, 13. Everybody take a look at that. Here, let me make these a little bigger. Those are kind of small, aren't they? Can I make it? Oh, I can't do it that way. Oh, it won't do it. Sorry, I tried. 13. What's going on there? Which property is that? Associative property of multiplication. There we go. Good. Okay, good. How about number 14? What's going on there? That's distributive, isn't it? Okay, what about 15? I heard inverse. Inverse property of, there we go. 16. What's that one? Commutative. Everybody agree? Commutative, because all we're doing is exchanging the positions of the things that are being added. $17. The dead giveaway is it's more than two things. What do you think? Associative property of addition. There we go. Good. What about 18? Inverse. Oops. Multiplication. Okay, what about 19? 19's a little tricky. What's that one? It's distributive. Good. And the key here is you don't necessarily have to start on the left side and move to the right side. We could go ahead and recognize that if I started on the right side and I distributed to 3, I'd get the answer on the left. You can go either way in an equation. Okay, you don't have to just read it from left to right. And then finally, what's that last one? Identity property of addition, right? Okay, good. All right, so last little bit. Name the additive and multiplicative inverses for each number. So what's the additive inverse of -8? 8. Good. And remember, all that is, the additive inverse, that's the same thing. That's the same thing as the opposite, right? the multiplicative inverse is the same thing as what? Reciprocal. So what's the multiplicative inverse of -8? Yeah, -1. Oh my goodness. -1/8. How about 2/3? What's the additive inverse? -2/3. What's the multiplicative inverse? 3/2. 6W, the additive inverse is multiplicative inverse. 1 over, yeah, over the whole 6W, right? Because the entire thing has to be flipped. Does that make sense? Okay. Square root of 10? Negative square root of 10, right? So what about this one? What's the multiplicative inverse? Yeah. You may be thinking, well, I thought there was no tenths in the basement, right? You can't have a square root in the denominator, and technically we shouldn't, but we're just going to leave it like that for now. We'll review that stuff later. Okay, one other thing I'm going to do with you guys with the honors class, I want to show you another really cool property. It's called the closure property. So here's how closure is defined. A set, so you always ask the question, is a certain set closed under a specific operation? Okay, so it always involves a set and an operation. So a set is closed under an operation if the operation always produces an output in the same set. Okay, so if an element outside of the set is produced, then we say that the set is not closed under that operation. So let's look at some examples here. Let's see if we can just look, we'll just look at 4 for now. Is the set of integers, is that closed under multiplication? Now, before you answer the question, what does that imply? If the set of integers is closed under multiplication, then that means that anytime I multiply two integers together, right, anytime I use that operation on two integers, what would have to be true of the result? It'd have to be, if it is closed, it would have to be an integer, okay? If I multiply two integers, I would have to always get an integer result. Is that true? That is true, isn't it? Anytime I multiply integers, I always get an integer back for my answer. So true. The set of irrational numbers are closed under subtraction. Now I'm going to ask you something else. How many counterexamples would you need to come up with to make that statement false? 1. You don't need 10, you only need 1, right? If I can think of one example where that is not true, then the set of irrational numbers is not closed under subtraction. We can think of lots of examples where it is true. Like if I said pi minus the square root of 2, that's irrational, right? Square root of 3 minus the square root of 2 is irrational. So there's lots of examples that would indicate, yeah, it's true for many examples. Can anybody think of one counterexample where it's not true? What do you think, Kylie? There you go. That's a good one. Pi minus pi, how about? Right? So this is false. And a great example would be pi minus pi equals 0, right? 0 is rational. Everybody agree? Okay. Questions on that? Does that make sense? Okay. I don't know if there would be any others. I mean, you could do square root of 2 minus square root of 2. I can't think of an obvious way that you could subtract anything other than what you started with and have that the result be rational? But that's a good example, okay? Whole numbers are closed under division. True or false? False. Somebody give me a counter example. 3 divided by 2. There you go. Okay. False. 3 divided by 2, right? That is not a whole number, is it? Odd numbers are closed under addition. False. Give me an example. 7 plus 1. In fact, any set of odd numbers you add are always even, aren't they? No matter what. So it's false too. Okay, we good? Normally with you guys, I would probably push through something else, but I want to give you a chance. How many people have started the assignment? Has anybody finished the assignment? Oh, okay, good. I want to. There were no closure questions though, right? Okay, I'm gonna give you a short one with a couple closure questions. I'm just gonna make it right now because I forgot I didn't put those on yours. So let me do that very quickly. And we may even, we'll see how much time we have. I might push into something else, but it's a Friday. Maybe I won't too. We'll see here. I'm going to pause.